All right, like I said, my name is Joel Stocker, and I work with the University of Connecticut's Cooperative Extension System. And I'm here with Kevin O'Brien. Want to give your title and name?
Hi, my name is Kevin O'Brien. I'm an environmental analyst with the Connecticut Department of Energy and Environmental Protection's Office of Long Island Sound Programs.
All right. We'll be kind of breaking this talk up in both. Oh, yes, and Juliana Barrett is sitting right in the background. You'll hear her voice every now and then. Whenever we get stumped, we always turn to Juliana. And Bruce Hyde is in the other room hiding altogether. But we're the four people working on this project. So basically this project goal is to conduct a GIS time series analysis using maps of the Connecticut shoreline from two time periods, from between two time periods, mainly the 1880s and 2006, about 100 plus years. And the goal is to provide a high-level, kind of a quantitative assessment of the Connecticut shoreline, both from a statewide perspective and from a localized perspective. And we use a piece of software called Digital Shoreline Analysis System, or DSAS, to do the analysis. There's an educational component to this project, which basically is educational materials, but also this webinar, and that's why I get to check this off as having done our job. Time frame for it has been about 1.5 years, and we're kind of coming to a close here in April 2014, and things should come together, and you'll start to see some results from this study. Here's just an overview of what we plan to talk about today, kind of guidelines for using this data, and obviously there's caveats built into that. Kevin will go over that in detail. Then I'll give you a little bit of background about how the study started and where we came from in the beginning, where we're basing a lot of our information on previous studies. Talk a little bit about definitions that we're using, and then some of the data sources and tools that we brought up. Also, Kevin will go into more detail about the processes and explain preliminary results, and then we'll try to show you some visual samples with maps that we put together. And then we always repeat the caveats, because that's an important thing with this project, no, with any project actually. So I'm going to pass it on to Kevin.
Okay, so as we all probably know, shorelines aren't static. They're always moving. So when we're looking at this from a data perspective, we're capturing a lot of different information that the shoreline is telling us. Cyclic and non-cyclic processes, so daily effects, seasonal effects, are all included in this, as well as man-made effects. We know, for example, beaches are nourished and graded, and shorelines are filled and developed. So all of these things are sort of implicitly built into this. We really had no amount of effort to go through and try to call out these things specifically. With the exception of a few large-scale development areas, mainly around the areas of Bridgeport, New Haven, and the Thames River, where we can sort of make some general assumptions that some fill has happened and sort of account for that in our results. And so the disclaimer here, a couple points. The data that's presented may differ from stuff that exists in other sources. And these differences don't necessarily mean that other sources are wrong or ours are right. Because what you really have to do is consider that what are the sources, how might other analyses have been undertaken, what exactly they're trying to say, and then, as always, the inherent uncertainty that's involved in these things. And then really probably the most important thing to think about here is what we're really looking at is trying to represent what's happened under past conditions, and really none of this should be used to do any forward predictions on what might happen in the future. So this is really sort of a historical trend analysis. So here are some suggested best practices. This is not limiting to everything, of course, but we feel that these materials can be reasonably used to identify areas that have historically exhibited erosion or accretion, identify areas that have shown a trend reversal from long-term to short-term. So that's something where it's trended to erosion over one time frame and then switched. Generally assess the speed or magnitude of change, or support additional research investigations or planning purposes. On the other hand, we should probably not be using this material to solely differentiate or explain what the cause of change is, or state with absolute certainty the magnitude or speed at any given location, and again, not to predict future rates or amount of change. And we've also added develop engineering or design plans with the asterisk that any attempts to do so really ought to go through and look at the underlying data first and make sure that the assumptions and the processes they use are consistent with whatever those engineering plans or designs might be used for. So back to Joel for some background on the project.
I will mention that one person has said their slides are not advancing. I hope that's not the case with other people. If it is, you can always just drop that into the question box so we know that other people are having that issue. Not quite sure what the solution would be. That might be something on there, and I hope it is. So anyway, just a little bit of a background. Back in 2010, the USGS did a shoreline change study for the entire kind of East Coast, all the way down from Virginia up to Maine. And that study was very detailed and over another like 100-year process like it was before. Okay, slides are advancing on some others, like Dave's. Well, he's down the hall. Of course, it's going to work for him. Hope it's working for others. Anyway, this study, they did analysis along all these shoreline features to identify the changes along these sections of shoreline over a whole 100-year period. And from that, we you can take out, you can look at a small section and identify what types of changes are taking place in those areas in detail. One thing they have out there is the luxury of these nice giant coastlines that are they're a little bit different than Connecticut, you might say. So I'll go on to the next slide here and explain that why Connecticut was overlooked, and Kevin's going to go into a little detail here.
Okay, so really when USGS is doing their analyses, they consider Long Island Sound a comparatively low energy system versus the rest of the coastline that they've looked at. So essentially they ignore it. The rates and values they may get for here really don't correspond well to other areas. So we really want to try to plug that gap, and that was really one of the drivers for doing this, to sort of look at what they've done, replicate it as best we can, and try to come up with values that are meaningful for us. Other couple of reasons are existing information on shoreline change rates are typically sparse. They can be anecdotal, relating to personal observation or institutional memory that can vary or change over time, or dated. The only statewide source of information that we currently have is a document produced by our office back before it was OLISP in the early 1980s, where they looked at erosion planning trends around about 1980 or so. And then recently there have been several stated or implied needs. There have been recommendations that have come out of the recent Connecticut Legislative Shoreline Task Force that address hazards and coastal change. And we always get questions from state and local regulatory planning groups about shoreline movement. Is it eroding? Is it accreting? And so on. So this is really an attempt to plug some of these gaps.
Yeah, and I'll take over again because Juliana years ago helped get us involved with making sure that Kevin and I would work on this and try to get Connecticut fitted into this, this analysis. And Kevin and I just took it on because we love this kind of work. So we did take on this project, and here's the area that this is the shoreline, obviously, Connecticut, and the 24 towns that we've worked with. There are over, if you just took a linear line of the shoreline, it's a pretty much 100-mile section of shoreline that's in Connecticut. And I'll show you a little bit later how, if you look at the actual features along the shoreline, it's a lot longer than that. This is the total shoreline distance that we took on in our project to study. Just a little background of what defines a shoreline, at least for this project, and basically for work that's like this. If you were to take, if you could have a snowstorm, which we had a few of them this year, and blanket the coastline with snow, and then have the tide come in overnight and reach its highest maximum, or at least the average high tide, melt that line, you would get an idea of the high water line mark. That's one concept of a shoreline that you could classify, at least when you're doing studies and projects. It's the one we're most familiar with. And when you're doing a study like this between different years, you need a standard shoreline, because otherwise your data is going to be mixing apples and oranges. So we're not using features something like this where you measure the like the changes like we had during the storms, the big storms, Sandy and Irene, where here's how, as far as the water reached in this case, in this photograph. That's not the shoreline we're working with. We're actually going back and using something else. And for our project, there are, Kevin might want to go into this a little more just to get an idea of what we're talking about here.
Sure. So we're very fortunate to have a really great set of data that's really configured very well to do this type of analysis, which are the Office of Coast Survey through NOAA's T-sheets, the topographic survey sheets. And these span back in time quite a ways, all the way back to the late 1800s for Connecticut. And when they define shoreline, what they're talking about is mean high water. Now there's a standard definition of that, which is averaging the 2 daily high water lines. In practice, when surveyors were out capturing this information, particularly on the Atlantic coast, it's really an interpreted line by the folks doing the surveys using the physical appearance of a beach. And really they're sort of looking at that line that defines the high water limit. So for the vast majority of information that we're using the mean high water line from these T-sheets. As it turns out, in talking with USGS about implementing this, we're also able to use additional shoreline data. Their rule of thumb is the more data that we can use, the better, and we can sort of account for some differences in what that shoreline is by adjusting how certain or uncertain we are about that. So they've recommended, and they've done this in California, to use the USGS topographic quad maps version of shorelines. And in these cases, what you're really sort of looking at is the wet-dry line, or the intersection of land and water as somebody interprets it from the source material, which in this case are usually aerial photos. Now in some cases, the wet-dry line may match fairly well with mean high water. In some cases, it doesn't. And that's the need to sort of adjust the uncertainty values on this. And we'll talk about that a little bit more in detail. But it's another source of data that we can use to fill in, although the vast majority of it is based on the T-sheets.
So in the long run, you're actually trying to come up with a standard shoreline that we can use, and there is that element of uncertainty when it comes to actual boundary is. But we'll talk about that in a second, how it can actually be still, the data can still be used. One question comes up is how far back in time can we actually measure the shoreline change? And obviously we weren't here for very long, in the long run. I'd love to go be pre-colonial before we even, or the European settlers even arrived. It'd be fantastic to know what the shoreline was back then and how it was treated and see what kind of erosion rates there were. But we really don't have that kind of data on the scale of, and nothing on the scale of the state at least. There might be some small surveys that people did early in the 1700s or something. Some of the maps, as time goes on, become more accurate. And if you look at like the 1824 map that here we have here, features are becoming more identifiable, and you could probably, in some cases, do some work if you had the time to adjust for at least local areas, whether or not things identify the shorelines back in those time frames. Maybe not with this map, but with other maps of that time frame. So it's getting closer to something we could use to measure the historic, the original shorelines that we start from, but we can't go very far back. In the 1880s, there were some national surveys they did. NOAA put together. That was a National Oceanographic Service back then.
I think it was Office of Coast Survey.
Office of Coast Survey. So I've got to change my acronym here. But they have done it. They did a coastline mapping project for all of the nation, to basically for navigation purposes. But it came out with a feature on that maps the shoreline. And I believe Kevin was saying earlier, they pretty much started this project somewhere in New England or even Connecticut.
I think they started around here.
Yeah. Just to give you some background on what these original surveys look like, if you can take one of the T-sheets from that time frame and look at an area up close, they're remarkably well detailed maps. They even provide a lot of upland information, but I'm impressed by what they had done back then. And all of it was done by on the ground. They didn't have aerial photographs back then, nothing at this scale. There were some later I think aerial photo started even in 1885 timeframe. There might be a few from balloons. But everything was done from the ground using triangulation and measurements where they could see it from the feature and then put it on a drawing that they had out there with them. And like I said, the detail is amazing, and if you look at something up close even further, you can see some of the data that he collected at that time. It has features on these maps that include the vegetation line and some of the T-sheets that they have and water line as part of what they surveyed. But they also, what we're interested in is that they surveyed this mean high water line that Kevin had mentioned earlier, where they made their decision on where that was. The advantage we have is that that shoreline has been digitized both by NOAA and Connecticut, and DEP did some digitizing of their own. So it's already in a format that we can use. That particular shoreline feature is in a digital format that we can now take and compare to modern imagery and modern data. And that's part of the importance of that is we did not want to do any digitizing, or we did not have the time or money funding to do the digitizing on our own, so we had to use existing data sets. There is existing GIS data for the shorelines up to 2006, and that's where you can see the comparison between these 2 years and how they work out. When we take that information and put on these levels of uncertainty for what we think the amount of error might be on those features, given the how long ago they were put together, we can now start with making decisions on how much has changed between these two features. In this case, down here this is down in Old Lyme along by Griswold Point area. In this case, about a 300-foot gap. That's a distance that, given our uncertainty, is definitely something we can point out as a real factor. So that's the kind of information we're working from. And we have these digital line sets for multiple years in Connecticut. Portions of the state have more than just the 1880s and some of the other intermediate years. But for statewide, we have basically the 1870s and 1890s were grouped as one time frame, and we have another statewide data set from the 1980s and another one from the 2006. So those are the 3 statewide data sets we have, but we do have information in some parts of the state that intersect other years. And Kevin will go into detail a little bit how that can be used in the analysis. We're not working with these interior coves and rivers that you'll see on these data sets if they ever show up on some of the pictures we're showing. That's just too, it's like spaghetti, and we're focusing on the outer shoreline system. So that's taken out of the analysis. So how do we process this information? In this example here, I've got an aerial photo from 2012 just as a backdrop, but here's down in Waterford area with 2 data sets from 2006 and 1880. We started by, within the GIS, making this thing called a baseline, which is a line feature that I had to work with Kevin to create that's offshore of every single line feature that we have in the data set, so that nothing, I'll explain why in a minute, but basically we have to be offshore of these line features, and that baseline has to be parallel to the shoreline for areas where we're doing our analysis. And we worked that out in a lot of detail, going back and forth, Kevin and I did, to come up with this latest data set. If you look at that in a little more detail, we take this baseline and the vector files that we have from the different years, and we run it through this program called DSAS. The software creates these transects that you see slicing through the years, and that, like I said, the transects intersect these shorelines. And then when you're finished running the program, the output that it creates stores the change measurements into these transects. So in other words, like you see here, you'll see the 1880 data set and the 2010. That line in between has information about how fast and rates and other information that's stored within each one of these transects. keep that transect, that little line in mind when it comes to what Kevin's talking about, because that's going to be the basis for a lot of our analysis. It's all stored in those. So we were able to run this program and do it for the entire state. And that's where the results are coming out, and that's where we're finally getting around to talking about it with a webinar here. I'll pass it on to Kevin to talk about the process a little more.
Okay. So before we even did anything, the first thing that we wanted to do was really try to ping on USGS and get their opinions, thoughts on in the methodology that they've used, what has gone well, what hasn't gone well, what are things to be wary of, be cautious of, do, don't do. And they were very helpful and forthcoming with helping us sort of craft our methodology. In terms of processing, it's about the same. They've gone above and beyond in terms of some of the analysis that comes out of that. We've essentially stopped at the processing part for now. But without their help, we would not have gotten as far as we are today, certainly. So very helpful from that respect. Secondly, we had to acquire all the shoreline data that Joel had mentioned. Like he'd said before, we're sort of working with things that have been pre-digitized already. We really didn't have time or funding to do data development ourselves. Fortunately, there is existing lots of data that we can use, so this was a very easy, beneficial step. We also wanted to do a fairly rigorous QA/QC on some of this information. And as Joel had mentioned before, we're talking about areas of certainty or uncertainty. And we've mentioned earlier that we know the shoreline is a movable object. And there's been published material through USGS and through FEMA that sort of give you an average amount of error that goes along with these shorelines. And it's usually defined by vintage or time frame, also by source material. And it includes things like errors associated by the surveyors in the field as they were collecting, errors that are associated with taking these hard copy original maps and converting them into a digital format, everything in between. So we have some values that we can assign to a plus or minus distance for these shorelines. And we've done that. And what we really want to do is sort of give a quick look through the coast. And what we're looking for are where we wouldn't expect a lot of change to happen. So rocks, rocky outcrops, permanent man-made objects. If the shorelines from way back in the day match up with that, then we can be relatively confident that that's pretty good and there's no systemic errors, an offset for some reason or some kind of error that's been associated with georeferencing or whatever. So in the case here, the example, I don't actually know where this is, but the blue line is the shoreline and sort of the pink crosshatch area is this range of uncertainty. So if you'll notice it doesn't really look like it matches up exactly, but that's okay because the overall trend fits. And if we assume that that shoreline can be anywhere within that pink area, we feel pretty good about that. So that's an example of something that we've kept. Here's an example of something that we've gotten rid of. So the very bottom of this photo has a shoreline that sort of goes out into the water quite a bit, doesn't really match up with any kind of shoreline that we're seeing. This is an area that we've extracted and removed from this so that we're not using it in any part of the analysis because we really don't feel it's confident and good enough. So the take-home message is we didn't just take the data and plug it in and start using it. We really tried to go through and do an assessment and keep what was good and remove what was bad. So as Joel had mentioned before, we used DSAS, which is a free extension to the Esri ArcGIS package. It actually exists as a free web-enabled tool now at this point, but wasn't available when we started this. But really what we're looking to sort of quantify and look at are two main things. One is how much has the shoreline changed, and you can think about it as how far has it moved, and also how fast has the shoreline changed, so at what rate is it moving. And for each one of those two categories, we're looking at a long-term rate or a long-term distance. So that's looking at all the data that we have going back from the 1800s to 2006, but also looking at a short-term change. And that's really going from about 1983 to 2006. So we can look at what a long-term historical look is and then a shorter-term look. And you'll see after in a few slides here what the results are. We have tables, charts, GIS data for individual points along the coast. These are the transects that Joel had mentioned. But we can also do some aggregation, and we can group those transects by town. We've also looked at them by areas of the coast that are geologically similar. And this was recommended to us by USGS. So we're able to find from a planning document that I had mentioned earlier that our office had done in the 80s, a breakout of the coast by similar geologic areas. So there's 7 different zones that you see here. Some of them are similar and some of them are distinct, but they basically sort of group things that are geologically similar. So when we look at some of those results and we can look at change rates and how much have changed, we can do them within these zones that are sort of self-similar. Okay, so in terms of how much has the shoreline changed, the main method that we're using here is net shoreline movement. So this is a hypothetical graphic example, but if you had a dozen or so or however many shorelines in a given time frame, you're really just looking at the distance between the oldest and the newest shorelines and ignoring the rest. And that gives you the net shoreline movement. We can look at the speed of that change or the rate of that change and answer the how fast it's changed by looking at a simple endpoint rate. And really that's nothing more than the net shoreline movement that we talked about in the previous slide divided by the time frame. So again, a hypothetical example here, but if that net shoreline movement distance was 76 meters over a 69-year time frame, then the endpoint rate that you get is 1.1 meters per year. So that's the idea of this, how fast has it changed. So some pros and cons in the positive category, it's very simple to calculate. And you can do this anywhere that you have data because really all you need is 2 shorelines. And if you don't have 2 shorelines, you don't have much to compare, so you're not doing anything anyways. And because of this, you can do it anywhere you have data. It's very easy to take a long-term endpoint rate and a short-term endpoint rate at all the places that you're analyzing and be able to do this comparative analysis. On the downside, since it only uses 2 shorelines, if you have others, those are ignored. They don't even enter into the analysis. So in some ways, the rate can be idealized. It also assumes that there's a linear fit to this. This is clearly not always the case. Unfortunately, the linear analysis is really the best that we can do at this point, at least on a large-scale statewide effort. Also, the rate can be influenced by how good or bad either one of those shorelines are. So if one of them is really good and one of them sort of stretches the end of that uncertainty range, that can affect the rate. And lastly, we really have no idea of how confident we are that the rate is. It's just a calculated value and nothing else. Conversely, or not conversely, but in addition, I guess, we can also look at a second way to look at rate, and that's by using a linear regression analysis. And in this situation, what we're using is a system that DSAS will take and try to fit the best possible line to the trend of the data that we have at that location. And that line's orientation and how well it fits with some of the data lets us also say something about how confident we are. And in this case, we, the users, get to say how accurate or confident we are in that information. So in the example here, we have a series of intersection points that the shorelines intersect with the transect. And the graph on the bottom is just a scatter plot of those points. So on the bottom you have time going from 1930 to 2010, and then the distance from the baseline. And you can kind of see that those scattered points kind of fit this dashed line, which would be the best fit line. And from that we can calculate the rate, which is the slope of that line. And those offset distance that you see there, some of them very minimal, some of them very large, are used to assess the confidence that we have. And that confidence is really just a measurement. So for example, in this case here, the rate is about 1.3. The confidence might be half a meter. So we would say that we would be 86% certain that the rate could be within plus or minus a half a meter of 1.3. So again, pros and cons, relatively easy to implement, especially if you have the software. It does use all of the shoreline data. So we're not looking at just the oldest and the newest. We're looking at all the data that we have in any given location. It gives us not only a rate, but an estimate of how confident we are in it. And again, we can specify that level of confidence. Now that's sort of a double-edged sword because we can set the confidence level very high and say we want to be 98% sure of what we're saying. The net effect generally is that reduces the amount of data that you get out of this. On the flip side, you could set it very low and use more data and just sort of accept a lower confidence range. And for what we're using here, we're using 86%. So it's a solid B. Not Dean's List, but not failing either. And then on the negative side, again, as with the endpoint rate, we're assuming it's a linear fit, and we know this isn't always the case. You do need at least 3 data points, and ideally more, to implement this. So these two things can kind of lead into the last points, where we can get inconclusive results in some cases. So if that uncertainty measure is greater than the rate, then statistically we can't say anything about what's going on there in terms of that rate. And that means that there may be areas where there's no output from the linear regression rate that we can actually use. So here are some examples of output. I'll apologize because the quality of these may not be all that great. But when you get to the pretty pictures that Joel shows, you're going to forget about all these anyways.
That's why I made these slides like this, so Kevin got these.
But the first example is basically just a summary table. So we have a grouping of long-term data and short-term data. We have information on net shoreline movement, the endpoint rate, and the linear regression rate. We have it aggregated by towns and by geologic zones. So this is sort of a nice compact comparative method to look at essentially the main points of all the output that we're generating. From that table, we can create some charts. So what we're looking at right now is a chart of how much the shoreline has changed over the long term, averaged by towns. So this is the net shoreline movement. So we have our geologic zones along the bottom, our towns on the bottom, and then a measure of what that average net shoreline movement value is for each town. We have the exact same concept in this slide, except rather than the long term, this is the short term net shoreline movement, again aggregated by towns and also indicating along which geologic zones we are. So these two sort of give a really nice overview at a statewide level of kind of what's going on in terms of net shoreline movement.
Yeah, and it's positive and negative, and some of the spikes, we'll explain a little bit about what the spikes mean in some cases.
Right. So we can also comparatively look at how fast the shoreline has changed. So this is a slide that puts together both the long-term and the short-term rates. So if you can make out the colors, the darker green color is the average long-term linear regression rate. And it may be a little bit hard to see, but there's a little kind of arrow bar that's associated with that. That's the confidence level with them all. The light green is the average long-term endpoint rate. So side by side, you can sort of look at it and compare what's the linear regression rate value, what's the endpoint rate value. And then the pink or the reddish bar is the average short-term endpoint rate. So you can look at what's happening in the long term and then what's happening in the short term. And areas that might be interesting are where you had a long-term trend that signifies one direction, say accretion, that's reversed, or now as in the short term is looking at an erosional trend, or vice versa. One thing that we should probably be careful to point out here is there's nothing in any of this information that's going to tell you exactly what the cause of that is. Could be natural, could be the effects of man-made activities, could also be some swirly or spurious data too. But at least when we have things laid out like this, we can sort of get a sense of what's happening in the long term and the short term and maybe use that to target some future investigations. So again, this is sort of the whole statewide deal. We can be a little bit more specific and detailed with some of the data that we create. So this is a chart that shows the net shoreline movement for one specific geographic area. So this is the central coast of Connecticut from roughly Madison to mouth of the Connecticut River. And each one of these lines is a data point that was generated by a transect in that area. So this is a more or less continuous look at all the data that we generated throughout this section of shoreline. If it's pink, it's negative, so it means the shoreline has been moving back. If it's blue, it's positive, it means the shoreline has been moving forward. We can pick out some geographic points of interest along the way so you can kind of orient yourself. Instead of just looking at towns, we have features like Hammonasset, Clinton Beach, and so on. And we can also, thought it'd be interesting to sort of look at the Connecticut River mouth towns, both in terms of what the Long Island Sound fronting shoreline was, but also the river fronting shoreline. This is really the only place where we kind of address riverine areas. So we've broken out Old Saybrook and Old Lyme into two pieces, so you can kind of look at those individually or together if we needed to. And this is the exact same geographic area, again, Zone E, going from about Guilford to mouth of the Connecticut River. But what we're looking at right now are the linear regression rate data. So this is sort of a measure of how fast the shoreline has changed. And the important thing to notice on this slide is while the previous one had more or less a continuous data set using all the transects in this area, you'll notice that there's some gaps here. There are areas where there's nothing. And the reason for that is because either the rate that was generated or the information that was generated didn't pass the statistically valid test, or there weren't enough shorelines in that particular area to actually generate the linear regression rate data. So this is a little less in terms of volume, but good in the sense that it gives us that confidence level that we can be somewhat certain, in this case 86%, of the data that we're getting here. And then one other thing to keep in mind, this is going to play into some of the visuals that you'll see upcoming. One other metric that we need to keep in mind is the shoreline change envelope. And really this is just the total distance between all the shorelines that we have. So nothing that generates or references time in any way, shape, or form. It's really what's the closest to the baseline and what's the furthest to the baseline. So this is sort of the universe of area that the shoreline is moving in.
And I'll cut in here just for the idea here with the shoreline change envelope. The reason we put the slide in here to describe it is because if you look at some of these transects, it tells you how far the shoreline has moved back and forth. It may at this time be maybe 100 feet wide, but the transect itself might be 200 feet long, and that's because at some point in one of the data sets it reached that point. So visually we have to identify that because that's what's used sometimes on our maps. So I'm going to go into a little bit of just the geographic display that we've attempted to make with some of these data sets. And I also want to point out that Kevin had those charts on there. They're hard to see here, but we're going to try to get those out as a PDF file or something that you can actually see the information on them in a clearer detail. But here's a map of New Haven area, and this is just something we wanted to show that when you take this kind of analysis and look at it with a quick look, where you just put these transects that we put on there in place and then identify in the transect whether or not it's a gain in shoreline or a loss in shoreline, you can get some pictures like this. We also have in our legend here a thing called where we've got his net shoreline movement that he described both in a positive form and a negative form, as where the sphere identifies kind of the amount of shoreline change that's taking place in that location on that particular transect. So here in New Haven there was a lot of fill, and it used to be open water at this place, and this, at least as a visual, gives you a quick picture of how much where the fill has taken place. And then each transect gives you kind of a number or distance. Just as another example of that, again, we're just trying to show, we're in the stage right now where we're trying to figure out ways to best graphically display this information. And this is, like I said, one example showing the urban areas. And here's Bridgeport area. New Haven's the one that's got the most fill in that zone. And then here's the Thames River, just another example of how an urban area might look with this type of data set that we have. As you can see with this, mostly with urban areas, there is not a lot of natural dynamics taking place. And that plays into what Kevin was talking about with the net shoreline movement and the endpoint rates. We did not really use these urban areas to measure rates of change because doesn't really apply when it comes to this type of an environment. So that would probably be taken out of that data set that he's working from. So here's another way to display the information. This does deal with the endpoint rates and the net shoreline movement. We've attempted to describe the endpoint rates in this case with different color variations on some arrows. The arrows represent, the length of the arrow represents that shoreline change movement I was talking about with a maximum kind of fluctuation of a shoreline at any point. And the color of the arrow represents whether the amount of the rate of change. The arrow represents the direction, whether it was negative or positive. And then the net shoreline movement is, again, drawn as a small sphere of varying scales to show how much change has taken place over that period of time. This is a sample out here, like I said, in Stratford, and you can see how the features play out. And we put it on top. In this case, I put it on top of a 2012 aerial imagery, but our data only goes back to 2006. But this image is a standard one that we have through the CT Eco website to give you a modern feel for what the landscape looks like. If I go a little more toward the west, this is between Stratford and Bridgeport, mainly in Stratford area. Again, another example of a good, this is an area where it visually shows up well, where you can start seeing the change, both in terms of the amount and the direction of change. Again, we're not describing why or causes. You might say, oh, that sand in this case is drifting off toward the west, but in some cases in some locations, most of the expansion of land is from fill, maybe from the dredging operations in the Bridgeport Harbor. And that's where local governments know the details about really what's taking place. We're stepping back and giving the broad view that maybe they don't have. So, if you look at this same area, here's another example of it back in the 1880s, just so you have a feel for what the original data set looked like. And if I go back, you can see what it looks like today. I was telling Kevin earlier it would be ideal if we had this kind of a thing looking forward, where we could see where the land's actually going to be in the next 100 years, but we don't. This is a little bit of hindsight going on back here. But again, the lines themselves start at the shoreline that we've identified, or they've identified on the early T-sheets from the 1880s, and they work their way out toward the 2006 data set and have the years that Kevin mentioned in between for some locations. Here's another example in Milford, Connecticut, which it's an interesting location as far as shoreline change. I tried to match up some earlier 1934 imagery to this area, and I couldn't find anything that was the same in either image. But you can identify here some, just by a quick look at least with this kind of information, where the shoreline has changed a lot and where shoreline has gained material. This snapshot does not tell you why why that's changed. And especially when you look back at the 1880 photograph, if you have these images in the background, you can start to see that it's not necessarily a natural environment. A lot of it is human-induced. We put things, a lot of it is fill material when you see a gain, and loss is more just erosion taking place. Here's a sample, just a quick look from Hammonasset Beach and Clinton area. Hammonasset, we're taking a real broad general look, but I know Kevin and others have done a real detailed study of the changes on shoreline along Hammonasset Beach. That's not what we're working on here, but he has more information on an actual study where they did detailed work on that. But again, this gives you an idea of what some of the changes look like back in some sections of the shoreline. And I'm showing you here an area that I've shown you so far, some areas where it's more dramatic, just so you can understand what the data can do or what it's doing. This is that same area back in 1934, so you can see what it used to be, and again, what it is now. And I just want to put a plug in. There's a guy, Michael Hauser from the Magic Library up there at UConn. Magic Library up at UConn. given me access, easy access to a lot of the 1934 and other aerial imagery that I've been able to at least then rectify and put in the background for both for understanding the information and then trying to display it later on for education purposes. Here's one more example in Guilford and Madison area, and there's been a lot of change in this section, at least along some of the marshes and coves where there's no bedrock. It's mainly just marshland that has moved in quite a bit. And again, in some areas along that, you can see there are still some homes, and if I had intermediate photos, you would see what has changed in those sections. This is the Griswold Point and in Old Lyme area along the outside the mouth of the Connecticut River, and several people have already seen this on previous demonstrations I did because we started this project about a year and a half ago, and the first thing that jumped out at us was Griswold Point, and so we've already done some demonstrations and visuals with this, and actually put a little story, or at least Chet Arnold's son put a story in the Racklines magazine on this location. But one thing about this location is very complex, and it both looks visually nice, but it can also make our data look have crazy arrows going different directions in some locations. And part of that's because when you look at the historical imagery in certain locations like this where it's very dynamic, the movement is not necessarily in one direction. And here's a 1934 photo where you can see that the movement is east to west, and that can change how some of the features look. So we'll be looking in more detail, Kevin and I, on some of these data sets where we see this jumping out of what we would expect, and either putting caveats in those locations or at least maybe taking some of that data out. But overall, it does give you a nice, good picture of what's taking place. Here's what the same area looks like as of right after Storm Sandy. This is November 6th, when NOAA did a little quick flyover. And something that I've put together just to, and I've shown some people the sample already, but the idea is to try to visually explain what we've been doing and show that what it looks like in real imagery underneath. I don't know if this is going to show too well in a webinar, but I did put together a website that I have a link to on the next slide. So if you can't see these things very well right now, you can go to this web link and do this yourself. I've set up a website that allows you to cycle through some of the imagery, with the data on the top of it. You can cycle through the imagery and see what it looks like over the different years and time frames. And again, working with Michael and others, I've been able to grab some of these images so that I can then rectify them in certain locations. In Griswold Point, I have quite a few years. I have 21 years worth of information, of images. But at least with this little web link, you can get some ideas on some visual aspects of what's taking place. And hopefully I'll be able to add more locations. I've added a few here. This is, I'll jump over to, just so you can see like that Silver Sands Beach area that I was talking about. Here's the 1880s, 1934 time frame, and you can start to see how things change there over time. I don't know if this is going to show up too well for some of you people, but again, you can come to this website on your own and look at it. And the point is with this is that again, you'll be able to get a chance to see what's going on. This was not part of this project initially. It just came out of it because I was trying to do a little more comparison to some of this imagery. And initially, when we first started, I thought we were going to be the ones digitizing these photos, but Kevin said, no, I already have the data. So this started basically as an idea to see the imagery and to see what we would have to work with, and it's taken off from there. So this is available. I'll get you a link to this site on the next slide, and then we can go from there. All right. Did you have something you want to point out there, or is that something? Okay, got it. So anyway, this idea of getting access to our results, we have, I just want to put this slide up here so you understand that we plan to get the spatial data and some reports, hard copy materials, at least in PDF format, together and have them available on, would you say Sea Grant would have a link to this, at least from Sea Grant, maybe to the Clear web server? And I believe we'll be able to email the web recipients a link to this when it's available. For right now, I have this temporary website that you just saw. If you ever want to go to it, it's Clear2. That's the site that we can easily play around and work with things on. Clear2.yukon.edu, and then Coastal Change. If you go there, you'll get access to what I just showed you and a couple of sites as we put things up. And hopefully if we can get some PDFs or any other documents, I'll try to put them up on that site. Time frame, Kevin and I were just laughing about this earlier because we were thinking, late April, we don't know how long it's going to take, but we'll try to get some information up there that people can use. And we always repeat our disclaimers. And do you want to read it again, Kevin?
Well, I think we can just,
it.
paraphrase here. You know, the important take-homes here are that we've approached this in one fashion. There may be other sources out there that are different. It's not to say that they're bad, wrong, or indifferent, because when we do this, there's a lot of different ways you can do it. There's a lot of different ways you can process the data. So if you're looking at different information, you need to be cognizant of those facts. And then really just to underscore the no-no here is we really shouldn't be using any of the information that's generated out of this to project forward on what things might be happening. This is backward looking only.
And also when it comes to, as we start handing out data, it's always the issue if we put something online that people are going to zoom in on something really closely. And if it gets something where you say, hey, this is wrong, then I say, all right, that's either get feedback to us or start doing a more detailed study for that location on your with work that you have, because this is an overview, but it's also something that's useful to get you started. We thank you guys, and if you have, we see some questions here. I'm going to try to get what we can, and Juliana says there's some answers she's got in her little notepad here, so we'll get back to it, and make sure you read the question too when you got something.
Yeah, there's a question here. What was the cost of your work? And I can tell you that the grant that we got from National Sea Grant was just for $30,000. That included none of Kevin's time, and I have to tell you that Joel put in an incredible amount of time on his own. Every time I talked to him, he'd been working on this project in the evening, on the weekends. So that really is not a good reflection of the cost.
A couple other questions. I think we may have addressed some of these in the talk, but there are two questions about why did USGS leave out the Connecticut coast and the North Shore of Long Island. That really is because as far as USGS is concerned, Long Island Sound in total is a lower energy system than oceanfront proper, which is pretty much the main reason why they eliminated that. So half of that is now taken care of, at least through this at a preliminary basis. I'm not aware of anything that's happened on the North Shore of Long Island, though, so that still may be a data void.
Yeah, it's interesting.
The question, how would you expect the data you presented to inform the state of Connecticut's recently instituted regulatory policy to promote a living shoreline approach to managing Connecticut's shoreline?
This is Juliana. It's not going to inform the regulatory approach, but it's a beginning to start to look at areas that might be appropriate for living shorelines. The University of Connecticut James O'Donnell in Marine Sciences recently was awarded a NOAA grant that includes trying to determine areas of the Connecticut coast that might be appropriate for living shorelines, and this analysis will certainly play into that.
And I'm going to respond to Megan's mention there. Hi, Megan from Milford area. I would love to be able to help with that. I hope we'll hope that there's some funding in the future for doing some more detail in certain towns, but also the idea that any help you can give us would be great when it comes to doing more detail if we get into areas like yours. And there's one last question here. Do you guys want to look at this?
So the question reads, are you planning on furthering your investigation to learn the causes of the erosion and accretion throughout the shoreline?
We would really like to do that. We have to just find more funding sources in order to be able to further this research.
And Megan says, are there any areas that found to be particularly stable? I would say Greenwich is pretty stable because they got a lot of money down there. No. But there's areas where there's bedrock, obviously just stayed right put. We haven't really pulled those numbers out as to where locations are for that type of thing, and we're that stuff we're starting. And Megan, we're just going to start teasing that information out if we can.
Yeah, on a global scale, the least amount of change, both in magnitude and pace, is in the western part of Connecticut in that sort of first geologic zone. Whether or not you want to use that to define particularly stable or not is up for grabs. But as Joel had mentioned, anywhere where it's really rocky, Brantford comes to mind, parts of Brantford, probably not going to see a lot of change there. So geologically speaking, rocky areas would be really stable.
And one last thing I'll emphasize with that is this is a measurement from looking straight down. So most people actually live on the ground and see things from the side, and you know there were changes that took place after these storms. So we're only measuring changes vertically, or at least horizontally along the landscape. We're not looking in this study at what's taking place from really on the ground at close level. So that's it. I think we're at our hour. If there's anything else we have to go through here, any more questions?
So there's one last question that's come through. Was any data you collected extremely surprising to you, or was it all essentially what you expected? I'll throw out my personal opinion. I really didn't come into this with a lot of expectations. I treated this more as a data processing and analysis task. So I could say no, there was really nothing that was terribly shocking to me, although it was very interesting to look at areas that we know change very greatly, like barrier beaches such as Griswold Point or Pleasure Beach or whatever, and be able to see exactly how much or how far they have moved over time. That was fairly interesting.
Right. And also from my perspective, having done this project, you're looking at everything up close throughout the project. So just overall, it's been very interesting for me to see other parts of the state up close. So that's it. I guess we'll close everything down here. Thank you very much for attending. And like I said, we'll have available information up on the CLEAR site to let you know when this is on video, or at least you can always email us if you have any questions further from here. Thank you very much.